All right, folks, we'll get started again. So before our break, we spent some time introducing and going through some of the rationale for what we're going to turn to now is why Bayes for measurement and measurement modeling in particular. And the way I'd like to do this is kind of take you through a little bit of history. Some of this has echoes of what Paul mentioned earlier this morning about how things are done in practice in different ways. But I'd like to kind of talk through different generations of psychometrics or generations of measurement modeling. The first one being add them up total scores. So this is kind of first generation. And again, this reflects some of my background in educational measurement, but I think the same thing applies to different disciplines. So this kind of generation is characterized by all the different people you're assessing. They get the same tasks or the same activities. What we are left with is counts of observations that are indicative of a construct. In education, maybe your proficiency, your algebra proficiency, or in other domains, an attitude, or whether or not you are afflicted by some condition. Comparisons or decisions are made based on those total scores. And really, there's a lot missing here. There's no notion of the nature of tasks. What's difficult or what's hard? Like what's an easy question, what's a hard question? What's a sensitive, what's not sensitive kinds of activities? That lurks outside the measurement model per se. There's no distinction here between the observation, the total score, and what I'll call the inferential target, what we'd really like to know. There's really no notion of measurement error, except when your score is different than you expect or want it to be. There's no probability-based reasoning at all for characterizing the evidence that you have or facilitating inference. Brown and Miss Levy called this intuitive test theory. A test is a test is a test. They're all the same. Or, well, a test measures whatever it says at the top of the test. Oh, this is a chemistry test. Okay. Your score is what you get by adding up the points that you got on the different subcomponents, like items or tasks on the test. Your score is what your score is, and there's some magical cut score for passing or achieving a diagnosis of some kind. And any two tests that measure the same thing by the definition, this is a chemistry test, this is a chemistry test, they're the same or can be made interchangeable, maybe with a little bit of work. I think this is the interpretation that most people have about assessment, as well as people in assessment policy have about what assessment is. The next generation incorporates notions of measurement error. From Lord and Novick's classical text on psychometrics, 1968, again in educational context, most students taking examinations are convinced that how they do on a particular day depends on to some extent on how they feel that day. A student who receives scores which they consider surprisingly low often attributes this unfortunate circumstance to a physical or psychological indisposition or to some more serious temporary state of affairs, not related to the fact that they're taking the test that day. Oh, this score is too low. That doesn't really reflect me. Test scores are imperfect. They're not exactly what we would want. There's a notion of measurement error. The distinction between the observation, say, students' performance on a test or something like that, and what we'd really like to know about them. This matters. Recognizing or acknowledging measurement error matters for inferences about those being assessed, as well as relationships with other variables. A little example I like to show, here's a perfect correlation between two variables, X and Y, perfect correlation. I'm going to hit every point with my regression line if I fit a regression line. Wonderful. Let's just now introduce some measurement error. So now just say for make it easy, the Y variable, the outcome variable is now measured with error. So there's some scatter. I no longer have a perfect relationship. My slope is going to be attenuated. My correlations and slopes are going to be attenuated. Measurement error is clouding the picture of the relationship between these variables. Classical test theory as a measurement modeling framework is a really nice representation of this kind of generation of thinking where we have the distinction between true and observed scores. Here's kind of it is an expression, or graphically, I like this kind of picture. There is a true score T for each examinee or person being assessed. That's their pure, the true score, the real value. But that's not what we have access to. What we observe, X, is a function of that true score, but is contaminated in some sense by error of some kind, a kind of measurement error. This is enough to get us a lot of psychometric concepts, things like reliability, validity, and so on. We can recognize and incorporate notions of measurement error and the unreliability that results in scoring. So here again, it's kind of from classical test theory. We've got true scores. I've got 3 examinees, Lauren, Matthew, and Elizabeth, and I've plotted where they fall on the true score scale. But our observed scores are not the same as the true scores. For each person, my observed score might vary around it by so much. That's what those little normal distributions are. If I give these people my assessment, Lauren's score might bounce around her true score. Matthew's score might bounce around his true score, and so on. The notion of measurement error. Some people nodding, I'll take it. Okay, how do we do some scoring here? Well, we give the assessment, we get the score, that's the observed score X. The likelihood is the form of a normal distribution. And so the person's score on the test is the maximum likelihood estimate of their true score. And there's a standard error of measurement, and we get all that stuff. Why use X, the observed score, as the estimator of the true score? Well, obviously it's related to the true score. It's a function of the true score. It only differs from the true score by some random error. And that random error is random, has an expected value of 0. We don't think things are systematically off. And after all, what other information do we have? I have the person, they take the test, this is their score. I don't know anything else upon which to base an estimate of their true score. Who could argue with this logic? We can. Psychometricians can. Here's Kelly's formula. Quick show of hands. Anyone familiar with Kelly's formula in classical test theory? All right, 1, 2, maybe takers. Yeah, it's been around 100 years. It's a better way to do scoring in classical test theory. It says for each person, for their estimate of their true scores, look, that's the left-hand side, the estimated or predicted true score, if you'd like. On the right-hand side, yeah, you incorporate their X value, their observed score, but not just that. In fact, you should take, if you look at the top expression, you should take their score that they actually obtained, the observed score, multiply it by rho, the reliability of the test. And then combine that with, well, 1 minus the reliability of the mean of the scores. This is a weighted average of the person's score and the mean from everybody taking the test, weighted by reliability. It's written in the second expression more like a regression-y looking thing where there's an intercept and then a slope times a predictor kind of form. It's the same formula. You can think about it in a few ways, which is you can start at the mean, the average, and then move towards the observed score. If the test is perfectly reliable, move all the way to the observed score because the test is perfectly reliable. To the extent that the test is not perfectly reliable, don't go all the way, stay a little bit closer to the mean. This is a long-standing tradition of estimating true scores in classical test theory, at least in the worlds that I operate in educational and measurement and related domains. This is a better way to come up with estimates of true scores by a number of different criteria. It's been around 100 years. This formula is actually an instance of Bayesian reasoning. If you specify a model where observed scores are normally distributed around, that is, errors are normally distributed, and you know the reliability and so on, and you do the Bayes inference, and you get a posterior distribution for each person's true score, the posterior mean, our point estimate or point summary, is exactly what Kelly's formula gives you. And the standard error of estimation from classical test theory, it's the standard deviation from the posterior distribution. It wasn't derived in this way. It wasn't even recognized as an instance of Bayesian reasoning for many decades. but it is. There's a connection here between inference about people and assessment and Bayes inference that I'd like to draw out now. Third generation measurement modeling or psychometrics, latent variables. So here's a little graphical or schematic of a latent variable structure. At the top there, generically denoted by theta, is a latent variable representing a construct of inferential interest. And there in the rectangles are x1, x2, x3, and so on, representing observed variables. I use circle for unobserved or latent, stuff I don't observe, and boxes or rectangles for things that I do observe, data I collect. My story here is that our observed variables, due to, say, measurement error, are imperfect indicators of the construct of interest. How you perform on the chemistry test items is not exactly the same thing as your chemistry proficiency, say in that context. Factor analysis, item response theory, latent class, finite mixture, diagnostic classification models, many families of modern psychometric models fit this pattern with extensions to the more complicated scenarios. Multiple constructs are different, but it's all this general pattern. What do we get from these kinds of models? We get a little bit more involved probability-based model for representing the situation, characterizing evidence, and facilitating inference. It's now not your total score. We often drill down to the item level, if you will, a little bit more fine-grained. We get a more nuanced conception of measurement error. We can get things like differential precision. So we can say, well, for people here on the construct, here's how precisely we measure them. For people here on the construct, maybe we don't measure them as precisely. We don't really get that easily out of previous measurement models. We get some notion of the tasks or activities. There are item or measurement model parameters. This is a hard item. This is an easy item in education. This item is discriminating. It tells us a lot about the construct. This one, relatively speaking, less so. Those are now part of the model. Those are parameters in the statistical model. And once again, we have a distinction between the observation, the X's, and the inferential target, say, the construct that we're modeling as a latent variable. We'll talk a little bit more about the connections with statistics. Some payoffs here. We get a lot of flexibility by using these models. Not everyone needs to get the same tasks. I was part of a conversation this morning about breakfast where talking about an assessment where there are 50 items and then one gets dropped. Okay, so do we take the score out of 50, out of 40? How do we handle those situations? That can be a challenge for classical test theory formally, well handled by latent variable models. Adaptive testing. Not everyone needs to see the same tasks or activities. Oh, I see you perform in this way. I'm going to ask you to tackle these problems next. Somebody else performs differently. I'm going to give them a different follow-up set. Adapting the assessment to the individual. More complex sampling designs. That is, if we're not taking simple random samples. And the idea is that inferences are really, for individuals, might be now based on the latent variables, not a total score. Theoretically, the latent variable is what we want. It's the sort of pure representation of the construct, no longer clouded up by all that measurement error stuff. This is a 3-beer topic, so we're not going to go into great detail, but what are latent variables? There's a few different ways to think about them philosophically. We could think about them from ontological, epistemological, or different traditions of causality or realism, sociocultural. There are a lot of different ways to do that. We don't have time to get into all that in our time together right now. The implications of incorporating measurement or latent variables for measurement have to deal with things like measurement error, the reliability, validity, and so on, as well as the inferences we make. But here's how I'll frame it. From a measurement perspective, latent variables are employed in our models to represent things, constructs, factors, whatever, that are not directly measured, but only measured indirectly, imperfectly by our observations. Typically, they're used to model variables we do measure, the observations more directly. And they're employed to explain away the associations we do observe via things like conditional independence. Let me drill into that a little bit. So where does probability-based reasoning show up in these notions of inference? Here's a quote from Charlie Lewis on reviewing the field on the occasion of the 50th anniversary of the Psychometric Society. Much of recent progress in test theory has been made by treating the study of the relationship between responses to test items and a hypothesized trait or traits of an individual as a problem of statistical inference. That is the marriage of test theory and modern statistics. A little bit later on, a quote from Miss Levy on the role of probability-based reasoning from statistical models. A properly structured statistical model embodies the salient patterns in the application at hand and spells out within that framework the relationship between conjectures, claims we'd want to make, and the evidence we have in support of them. It overlays a substantive model for the situation with a model for our knowledge of the situation, so that we may characterize and communicate what we come to believe, both content and conviction, and why we believe it, our assumptions, conjectures, evidence, and the structure of our reasoning. Assessment is an instance of evidentiary reasoning. Perhaps the two most important building blocks of mathematical probability are conditional independence and Bayes' theorem. What is this conditional independence business? From Pearl, conditional independence is not a grace of nature for which we must wait passively, but a psychological necessity we satisfy actively by organizing our knowledge in a specific way. Translation, we don't wait for this to happen. We build our model of the situation so that this happens. An important tool is the identification of variables that induce conditional independence among observables. If these variables are not in our vocabulary, we create them. In medical diagnosis, for instance, when some symptoms directly influence or we might think are correlated with one another, we invent a name for that, a syndrome, complication, pathological state, and treat it as a new variable that induces conditional independence. Here's the model for medical diagnosis. I have a bunch of things I can observe. Is the patient coughing? Is the patient sneezing? Does the patient have a fever? Do they report having a sore throat? And all those things are correlated with one another. Not a very useful model, according to Pearl. Instead, we introduce a variable, a syndrome, a complication, a pathological state. And our story is that all those things that we observe that might be correlated, they are explained by their dependence on this introduced variable. Conditional on this new variable, they are rendered independent. What a coincidence. That's exactly the form of our modern measurement models. This is not a coincidence. Okay. So here is our model setup. There is a particular flow, if you'd like. You can read it as an expression. There's that conditional independence expression. The distribution of all the observations, all the x's given the latent variable, well, I can factor into going one of them at a time. That's the conditional independence assumption that lurks behind so many of our models. There's a particular flow. Look at the directionality of the arrows from the latent variable, the unknown parameter, down to the observables. What about scoring or inference? Well, we got to go the other direction. We observe the x's. That's the observed scores in an assessment. We need to reason back opposite the flow of the model setup. We need to go back the opposite direction to reason up to the unknown. In this case, the latent variable. Okay. Everyone see this? Like we got to chart our course the opposite direction of the flow of this model setup. What is our mechanism for reversing that directionality? Bayes inference. There's our model. In blue, we got a prior distribution for the unknown parameter theta, somebody's construct or proficiency or true score, however you want to think about it. That's what we think about before we observe the data. We have a prior distribution for that. And then we know we have observations that depend on that parameter. That's the x's depending on the parameter theta. And that captures the evidentiary thrust that we get from each of those observations. That's what a measurement model captures. How do we go back the other direction? That's precisely what Bayes inference can do for us. Given the data, given the values for the x's, what do we now think about the unknown parameter? That's the posterior distribution for the unknown theta given the data. So from this framing, Bayes is a very natural argument to make from reasoning from the observed data back to the unknown constructs of inferential interest. We can extend this to incorporate and talk about other features like measurement model parameters. We know that the evidentiary quality of some of our observables differ. This assessment or this test or this task or this item gives us better information than this one. Can we build that into our model? These things are more reliable. These are more sensitive to the presence or absence of some. Yeah, we can build those in via measurement model parameters. All that does is just make our model a little bit more involved. We have measurement model parameters for different forms. Again, factor analysis, item response modeling, Bayesian networks or classification models, they all have different forms. But just generically, there are these measurement model parameters that capture the evidentiary quality of those observations. Okay, so our picture just gets a little bit more elaborate. Each of the observations not only depends on the construct for each examinee, but something to do with the measurement quality as captured by these parameters for each of our observables. So if we would like to have inferences about those parameters, okay, stick that in with Bayes inference. We get a posterior distribution for people, their constructs, or the latent variable of interest, as well as understanding the measures themselves in terms of the measurement model parameters. The same logic applies. This is a super quick tour of modern measurement modeling at a very high level. Why Bayes for this? Well, I'm just going to skip over all the why Bayes stuff we already talked about. All the things we mentioned earlier this morning port over to why you might use Bayes in measurement modeling. All those same reasons. So now, okay, why Bayes for measurement? What additional reasons do you have? The recognition of measurement error. What we observe might be an indicator of what we'd ultimately like to know, but it's imperfect. Our observations or observed scores on assessments are not the same thing as the construct of inferential interest. And the different ways we might measure that construct of inferential interest will vary in its quality. We'd like to acknowledge, capture that, and understand it. This is what measurement modeling does. In the presence of measurement error, we can get better characterizations of those being assessed, as well as relationships to other variables, the measurement quality itself. There are deep connections between Bayesian inference and measurement modeling. One that I've just mentioned was the connection to Kelly's formula for scoring in classical test theory. There are others as well. What I'd like to leave you with in this regard is that notion of we set up a model a particular way, from parameters down to data. You've been doing that your whole statistical life in some way, shape, or form. We then reason by reversing that flow from data back to parameters. What is the mechanism for reversing that? Bayes' theorem. There are other connections. If folks are interested, happy to talk about things like exchangeability theorems and so on like that. But in preparing this, I want to go through what are the ways that I know of in measurement modeling in particular that Bayes has been particularly advantageous as a scoring mechanism for reasons we've talked about, or more generally, how to express beliefs about people and situations probabilistically, as an updating mechanism, as data roll in, updating our beliefs, as a tool to rein in or regularize estimates. We've talked about those ideas already. A hierarchical approach to model construction, borrowing strength from different people or situations, allowing us to work at different levels. Integral part of decision-making. In education, things like tutorial systems that say, given your performance so far, here's what we recommend you work on next. As a way to manage uncertainty due to measurement error and other sources. As a really flexible approach that embeds measurement models in larger models to capture salient features of the situations, allowing us to build models that might be under-identified by frequentist perspectives that don't pose a problem to Bayesian inference. A little bit of a look ahead. One of the things that I'm particularly excited to be a part of this conference is thinking and learning about more and new kinds of data, including data that are in more open or ill-structured settings. The vast majority of assessment as played out in the worlds that I know is very isolated. Stop teaching, make the students sit down, take a test, end test, resume teaching. It's a sort of disjointed process. The world is shifting to a much more integrated process of how assessment goes on the fly, sometimes called stealth assessment. We don't stop other activities to gather information about people and make inferences about them. Instead, it's more tightly integrated. Assessments that occur in social or collaborative settings of some kind, rather than thinking about it as reflection of the individual, more of a socio-cognitive perspective says there's an individual or perhaps a group acting in a particular context. And that context matters, or their background matters for the inferences we'd like to make. Again, I was part of a really nice conversation this morning over breakfast about cultural differences and how certain assessments might be attuned to one culture but not another. Those differences matter. We need to do better at understanding and building that into our analyses. And really, I'd characterize this as a broader shift in thinking for future generations of measurement modeling, not to thinking about a test as a test as a test, and that's the answer, but to thinking we're engaging in a process of evidentiary reasoning about people or other actors situated in a particular context. We are subject to constraints in our work, but we want to acknowledge them and still try to do the best that we can. I hope I've gotten us back largely on schedule by doing this. Thank you for your engagement and attention. This is how to contact me. I'm around. I'll be in the work group. So I'll be here. I'd be delighted to talk about any of these things, beers or not. But this is also how to reach me outside of the conference if you'd like. Sure we are with questions or time, or if we want to. A little bit.
So not zero.
Non-zero. Okay.
We have a mic.
Zero is okay too. Zero is a good number. Yeah.
So, hold on.
Okay.
It's a two-edged sword. Yeah. Without one,
So do you think this, I think I already know the answer to this, but the non-determinacy problem of factor scores, can Bayes help in any way solve that problem?
Yeah, so the question is, what about the indeterminacy of factor scores, which in factor analysis models, there is an indeterminacy in the sense that there are different ways and frequentist traditions to arrive at factor scores. They're not the same. And in some sense, there's an indeterminacy there that needs to be resolved. And the question is, can Bayes help with that? Yes. As far as I see it, as from my perspective, there's no indeterminacy problem at all from a Bayesian perspective. The solution, if I were to offer one, and I recently wrote a paper on this, is just use Bayes inference. I don't need to worry about all those things. I think the indeterminacy in factor models is a function of one perspective on thinking, a frequentist perspective that I don't think is suitable. If you think about, let me just go to the picture, then I'll conclude. Oh yeah, there it is. If you go to this picture, we're reasoning back from the X's to the factor scores, if you will, and frequentists say, oh, we got an indeterminacy. It's not obvious what the right way to do it is. I say, well, in latent class analysis, which is just a discrete latent variable instead of a continuous, what do? Since the invention of latent class analysis, we've done Bayes' theorem. In item response theory, what do? We often use things like EAP scores, which are posterior means from Bayes. In multi-level models, of which you can think of factor analysis as a kind of multi-level model, how do we reason back to those effects? It's Bayes' theorem. Same thing in factor analysis, no problem here. So yeah, my answer is I can give you the reference to that. Just you just have to excuse all the typos, but otherwise articulates my position on the matter of straightforward.
Great, thanks so much. And that gets us back mostly on time. So I wanted to welcome you all back from lunch. Welcome to